the others come in. So we will continue with the idea of rheology and rheological modification. So a few things, right? So we ended last session with the idea that yes, you can do all the rheological tests. You typically will do the tests on pastes. And when you have to do concretes or when you have to actually print, the printer also becomes part of the problem or the solution. So you have the mix that you have tested, you print it, and you evaluate what the correspondence are with the properties and the printing. And that's why I gave you the example of a ready mix concrete guy who will have an M30 mix made. So similarly, you know that this is printable, but then depending on the situation, depending on your material, your printer changes, depending on environment, you make whatever minor changes required to ensure that your structure is extrudable and printable. Is that idea clear to everybody? That we are relying on a rheological measurement as your fundamental measurement to go with, for which you make correspondence with a field printed material made out of this paste. The rest are all correspondences that you're making. So that when the paste changes, you know how else it's going to change. Right? And that's how you make those changes. So now what else can you do to change the rheology? So here is one method people have tried where continuous CO2 injection. I mean, it is touted as a method to utilize CO2 in curing. I mean, people love to use CO2 in whatever you want. So if you inject CO2 into the nozzle, as the mortar comes through, you have CO2 coming in. That will create some precipitation of calcium carbonate. You will get so if your material was not completely extrudable, you will get more of CO2, calcium carbonate precipitation, get a little more rigid mix to come out of it. That's the idea. That's theoretically what it is. But the amount of calcium carbonate that's going to be formed is very, very, very small. This is a nice laboratory experiment. It's very difficult to see it actually working in practice efficiently, but nevertheless, one method that people have looked at. There is a CO2 flash mixing where you inject CO2 at the auger, at the nozzle, and then you extrude the filament. Again, same idea that you get some calcium carbonate precipitation. And here is how it is. Calcium carbonate reacts with calcium hydroxide. You form some calcium carbonate. CO carbon dioxide also will try to, because of the gaseous state of CO2 and the way it changes the solubility of ions, it will make a little other rheological changes as well. Nothing huge. And then if you have a 2K printing system where you can have another material that's added, you can control material deformation and collapse. You can add calcium hydroxide like an admixture. You can get stiffening and setting faster. So lots of different methods, again, depending on how you want to use it. Extrudability, we talked about, what is extrudability. So that's a ram extruder. That's a screw extruder. This is the most common type that you see where the material comes through and extrudes and then comes out of the nozzle. And then you get print whatever shapes that you want. Buildability is the process by which you build up layer after layer. And again, we talked about what properties you need for that. Challenges, and here is where we are going to get into the next set of lectures: optimal yield stress, structural recovery, thixotropy. You heard about it yesterday. We'll talk a little bit more about thixotropy. But how about structural recovery? So buildability is a function of both yield stress and thixotropy. Material thixotropy also plays a role in how well you can build up the layers. So the way to look at is, so this is actually a nice schematic of how we can think about what are the post-printing requirements. The moment you print what you want, right? Your yield stress, you have an initial yield stress. You want the yield stress to build up, or you want the load that you want to be resisting keeping on increasing as you add more and more layers, right? And your rebuilding kinetics also has to increase so that the load that you have to take care of is taken care of by the development of kinetics in the material that eventually leads to formation of material strength. So this is like an envelope. You never want this stepped line to go beyond that blue line. You see that? You want this to be lower, or rebuilding kinetics, and how much ever yield stress that you have generated should be higher than the stress that's added on layer after layer, right? You have to be within that zone. And if you're really, really good, you want that to be very close so that you have very optimally made those. You don't have excess strength in it. You don't have excess properties. You have designed it really well. That's the optimal way. That's what we will talk about. Again, coming back to the same picture I showed you earlier, because the next set of slides I'm going to talk about is in the realm of extrudability and buildability. So we will start with this one more slide. I'll just skip that. So this is about, we talked about particle packing, material design for printability. And now what we're going to do is really rheology apply to 3D printing. So lots of you asked questions. How do you relate whatever you have to what is printable? Lots of those will be answered now with rheology applied to concrete 3D printing. So everybody comfortable with the idea that the rheological demands in 3D printing are different. It changes from time to time. You need a delicate balance between flowability during printing and strength after deposition. Again, the extrudability and buildability, I really explained here. Extrudability being flowability during printing, and buildability is a strength after deposition, right? So those are the two things that you want. A material needs to be a liquid like pseudo solid to be pumped and extruded, but must quickly become a rigid structure to support its own weight and subsequent layers. So far what we have talked about, or mostly what we have talked about, are about the characteristics of the material in terms of particle packing, the yield stress, the viscosity, all of it that you test and characterize and keep ready for this process to happen. Now we are going into the process. So if you think about getting ready for swimming, if you are a swimmer, right? You go take a shower before you jump into swimming pool, get the right gear, all of that. Now you're ready to go into the pool and get extruded and built, or however it is, right? So what happens when the process really happens? Lots of preparation, lots of understanding what goes behind packing of particles, what is rheology, how do you test? Now you get into the nozzle and figure out what's happening right there. Okay. Static dynamic yield stress and thixotropy should be controlled through mixed design. So this is what we will talk a little bit more about, static and dynamic yield stress as well as thixotropy. Oops. So each stage imposes distinct, often competing rheological demands. What we need is successful material delivery to the print head, which means if you're pumping it, the material should come to the print head in a homogeneous, nice fashion. It should come through the extruder and extrude it nicely in a continuous fashion, and it should be able to build up steadily without collapse and damage. So that is the entire process that you want to think about. I've showed you this picture. So extrudability, how much time period you can extrude, the open time, how much material will keep the yield stress and plastic viscosity for it to be extruded out, and then how well you can build up and the structural buildup. So here are some videos that, let me see if we can show you those videos. So here is how you are used to seeing concrete generally, correct? That's what you're used to seeing concrete. You vibrate. That's your regular concrete. That's what you want. If something goes wrong, you can vibrate. You can take it off, put it back again. You can reconsolidate, revibrate. You can do all of that. But in 3D printing, what you need is, you need it to be extrudable. So this is extrusion. If it's pump, oops, I did. If it is pumping, if you're pumping it, this is how you need it to be pumped. But extrusion will have different demands. So here is pumping, concrete flowing through very nicely. But then you don't need just that. You need this as well. You need it to be extruded into layers nicely, and you should be able to build up eventually. So these are the conflicting requirements and demands that we have to think of. Uh, Material delivery phase, particularly when the material is pumped, what do you need? So again, guidelines. All of these, please remember, whatever you see are guidelines. These are not truth set in stone. Your material, depending on your environment, depending on your type of printer, might have differences that you have to work out on your own and set it ready for your purpose. But here are some guidelines. Like your mixer proportioning, you have guidelines. Go do a trial mix and make sure that everything is correct, right? So you have all of these are guidelines for you to do before you do your trial mix. Viscosity and yield stress must be sufficiently low to ensure smooth flow while preventing segregation or blockages. Very high viscosity, it'll flow very quickly. You don't want that because you don't have time to build up the strength after that, so you don't want that. Very low viscosity, you will have difficulty flowing. Very high yield stress, you will have difficulty extruding. Very low yield stress, it'll just come through. You won't be able to develop the strength to build up. So higher yield stress is desirable to maintain the shape of the extrudate and avoid collapse. Structural stability is essential to prevent immediate collapse. Issues look for excessive layer spreading or drooping. So if you have a layer and you put another layer on top, you don't want it to spread out and droop too much. Things to look for. Again, like I said, guidelines. Okay, let's look at some examples. Hopefully these videos will work. Okay. Oops. Why are they not working? Oops. It came and then it went. Maybe we should close it and reopen the slide set. Yeah. Yeah. Open it, close it and reopen it. Close it completely and then maybe reopen it. So, and post extrusion, that video also doesn't work. Right, post extrusion. So, at before extrusion, whatever yield stress and plastic viscosity. Post extrusion, once it's extruded, you want the mix to rapidly gain stiffness, allowing it to support the superimposed loads. That determines whether the structure can maintain its shape throughout the entire printing process. And then that is important because once you have extruded, and it has to retain the shape without drooping, without changing its shape, because that determines what the entire structural stability and properties of the build-up layer are, right? So it's important that once you extrude it, those properties are all efficiently maintained. So here is a summary of a lot of different characteristics. Again, everything kind of a summary of everything that we have talked about with respect to rheology. Buildability, you have to retain the shape and form after being extruded or deposited. In terms of rheological characteristics, what do you need? static yield stress should be more than the supported load calculated using failure modes. We'll show you a few failure modes as we go through to see as you build things up, how are they likely to fail, correct? So if I put one layer and I put another layer and another layer, if the bottom layer can't take the weight of that, it'll just collapse, right? The bottom layer will just slump and collapse. If I'm able to build up, but one layer here thinks, you know what, I'm not really able to take my load if I try to fall down. Have you seen all these cereal boxes that are kept stacked up in your grocery store, one after the other? The top one is just turn one on the side, give it a slight deformation, everything else will fall down, right? The collapse, yielding collapse mechanism, the buckling mechanism. So which ones will control? We'll talk about that using whatever failure modes. Extrudability, you should have it flow smoothly through the printing nozzle without clogging. Yield stress is an important characteristic there. Flowability, degree of flow that you have. Literature shows empirical correlation between yield stress, viscosity, flowability. So you can use some of that to determine what you will need. Pumpability, yield stress and viscosity that you know from regular concrete. That's what we use a lot of. The segregation resistance, yield stress and viscosity is related to segregation resistance. Thixotropy, we'll talk more about thixotropy. Removing applied shear stress and shear rate used to calculate what's called the hysteresis area, which will describe the thixotropy of the mix, and workability, yield stress and viscosity. So again, yield stress and viscosity explaining so many different things, but context matters. In all of this, it's context that matters. When are you measuring? What level are you measuring? And are you translating it to the field for whether it's extrudability or buildability? So get this big picture under control. So printability, both extrudability and buildability, is governed by yield stress and plastic viscosity. Like a broken record, I've been telling this all the time, right? Buildability and extrudability related to yield stress and plastic viscosity. Why yield stress and plastic viscosity? Because that's easily measurable. You can have a protocol to measure it. Once you measure it, you know what that means, and you can use all the parameters that you get out in your printer to be related to these parameters to get your black box ready, which you can change as and when you need it. The whole idea of doing this is to make sure that you control your processes and create some kind of an evolution to how you do this, so that the next mix doesn't have to go through all of these again. Right? You have a database, you have a set system to design and develop this. So here is time dependence. What happens if you mix immediately or extrude immediately? Not bad, right? That mix that you have is able to extrude even at 30 minutes. So you can say that this mix has an open time, or a time that it is extrudable, between 30 and 45 minutes. What happens at 45 minutes? Is it extrudable anymore? No. So at about 30 minutes it's extrudable. Now, if I make a lot of mix and my printing rate is very slow, and I'm not able to print this entire mix either because of printer constraints or because of layer size constraints. Somebody told you, I need a really well-defined, very tolerance controlled structure, very fine, needs to be very smooth. You need to have thin layers so that it's all very nice. Then you make a mix and it'll take a lot of time to use that mix, right? Which means how much time can you use the mix that you have mixed once? And now your question of how fast you're able to print. Now you'll know that you might have a mix that's extrudable if I print at 10 millimeters per second, but that same mix will not be extrudable if I do 25 millimeter per second. Can you think of that? I do it very slowly, it'll come out. I try to print very fast, it'll break. Now you're the question of how much does printing time, that is printing speed. It is a function of layer thickness. A thinner layer might extrude even if it is printed slightly faster, but if you increase the layer thickness, that might break. Now you see now the material properties, the printer properties, now we are introducing one more set of variables, which are the printing parameters. It is not just the printer now, whether it is screw or ram or auger or whatever way. Now it's about, or the nozzle size, it's about how fast are you trying to print, how quick are you trying to build up. You get now the third variable in this process. So what's the first variable? All the material properties. Second variable, everything that has to do with the printer, the nozzle size, the printer screw, ram, whatever kind of extrusion process you have. What's the third variable? The printing process. So material, printer, and the printing process. For printing process, open time becomes an important issue. When can you actually print? So this mixer now at 45 minutes, it's not printable. So now what you do is at 60 minutes, I'm not able to extrude at all. So what I do, I take it again and remix the whole thing. I can do a little bit more. So now in your mix, am I ready to take that risk and say, let me mix 1 cubic meter. I know I'm going to extrude only very slow, but in 40 minutes, I can remix once more and put it back in the extruder head. Are you willing to take that risk? You may, because if you're not saying that, no, I cannot, then you're throwing the material away. Right? Now, what you need to know is, are you able to do that? Do I know the properties well enough to do it? If I can, remix and do it. Again, just as an example. There are several other ways of doing it, but just as an example. So it's one way of thinking, how does the printing process influence? Tomorrow we'll see more about this in mechanical properties, about layer sizes. I printed a size of 10 mm versus 20 mm. How does mechanical properties change? Same material, right? Do you think it'll change or not? We'll see. Suspense. I showed this. So can mini slump test be used as an indicator of yield stress? As in the morning you saw that yes, slump is an indicator of yield stress, so you can do that. Now, what is yield stresses? We have talked a lot about yield stress. I want to make sure that we get this very correctly. Yield stress is generally defined as the stress required to initiate the flow, right? Now, we are going to do two different variants of it. Typically, what you tested yesterday, you typically did a dynamic yield stress or static. Which one did you do? You did static. We did it with time? Constant shear rate. Okay. So you did a constant shear rate. You did a static yield stress, which is a good indicator of how much buildability you can get. The dynamic yield stress that you do on a strain rate growth test, for example, if you build up from a strain rate of 5 to 100 and you take the up or down ramp and take the slope, when you get the dynamic yield stress, that is a stress that you find to maintain flow. A suitably low dynamic yield stress is required to be pumped smoothly through the mix. So pumping requires a suitably low dynamic yield stress. Building up requires a suitably high static yield stress. And static yield stress, so a stress growth test where the material is slowly sheared until flow begins. You measure the static yield stress, and a flow curve test where you do the strain rate ramping up measures the dynamic yield stress. Again, protocol differences, you're measuring two yield stresses, which are, so if I do shear rate ramping, up curve, down curve, I do the straight line, I come here, that's my dynamic yield stress if I do a shear rate curve. Whereas if I do a shear stress as a function of time, wherever it gets to maximum is a static yield stress, and then the flow continues unimpeded. So that's the static. So this is for buildability. And if I look at torque versus time, I needed to overcome a certain resistance of the material to be able to make it flow. And then once I do it, the material flows at a constant torque or stress. That's your dynamic yield stress, whatever I need to overcome. Good. So two different terminologies. Now, thixotropy. So now we get to the idea of thixotropy. Again, you heard this yesterday. This is the time-dependent reversible changes. It could be change in yield stress, it could be change in viscosity, it could be change in storage modulus. Any time-dependent change in a rheological property that is reversible is called thixotropy. Includes structural breakdown and buildup. So if I remix, I showed you this example of I remixed the mix again and it was able to extrude. What happened when I remixed it? It's a behavior, thixotropic behavior that you're seeing. When I remixed it, it's able to go back to the properties. I can redo it, which means my material is thixotropic. A non-thixotropic material will not allow me to remix and get my shape back. And if I try to remix after an hour and a half, you might be able to remix, but nothing will come out. You cannot extrude. So the material is thixotropic only for a certain time. And that time-dependent change in properties is called thixotropy, and it influences. So one of the most important applications of thixotropy is in pumpability and formwork pressure. Self-consolidating concretes, for example. When you have concretes that flow like water, it influences the formwork pressure much higher than a solid. Because if a solid, it's all the weight is going down. If it is a liquid, it is applying a lot of pressure on the formwork. So if your formwork is not very strong, a liquid-like material will fail. And you should have heard examples of grain silos failing when you put in a different grain than what the silo was designed for because of the differences in pressure that was not designed for. So again, the idea of formwork pressure. So thixotropy, what you do is, if you do a shear stress as a function of shear rate, one of the ways to do it, so you do the up ramp, down ramp, and the area between it, and you find out what shear rates you want to use it. The area is between the up and down ramp. What are you doing when you go in the up ramp? So I've taken a cement paste and I'm shearing from 5 per second to 100 per second in a ramp rate. What am I doing while I'm doing it? I'm breaking down that structure, correct? See that? So slowly at 5 per second, my shear rate is slow. And then the next ramp is 10, much faster. 20, even faster. 100. By the time I get to 100, I have broken down my structure. So my up ramp is an indication of breaking down of the structure. And then I keep some rest time and I slowly come down. Right? I slowly ramp it down. Which means with time, I'm now not disturbing it that much. It means what am I doing then? Building up. So if it is not building up at all, I'll come back along the same line, right? Along the shear stress versus shear rate, I'll come back along the same line if I'm not building up. But if I'm building up, you will see that difference. You will see a structure building up. The area under it is called generally a simplistic measure of thixotropy. There are better ways to measure thixotropy as well, but this is one way of measuring thixotropy. This is a short-term thixotropy because I am doing whatever instantaneous. I mixed it, I'm doing my test instantaneously. That is thixotropy at time 0 or time whatever, very short. I can do the same test after half an hour of mixing. After an hour of mixing, after 2 hours of mixing, the build-up and the breakdown will be different, right? The area that you get under build-up and breakdown will be different depending on the thixotropic qualities of material. If the material has a higher level of thixotropy, you are able to build it up much better. Is the idea clear? I'll show you some more examples as we go through. So, thixotropy enables the dual contradictory requirements of pumpability and extrudability. Pumpability, when subject to a high shear stress during mixing, the material's internal structure breaks down, resulting in low viscosity and good flowability. So we talked a lot about breaking down of the structure yesterday when we talked about yield stress, right? So now that is low viscosity, good flowability, prevents blockages, continuous smooth flow. Good? That is when you are doing a high shear stress during mixing. Immediately after extrusion, when the shear stress is removed, remember when it comes out through the nozzle, there is shear. And the moment it comes out, the pressure drops. There is no pressure, no stress at all, right? When that happens, the material is at rest and its internal structure is starting to build up. So, what are we building up? We are building up yield stress. We are also building up, we are recovering viscosity, right? So, we can do both ways to do the test. So this leads to a quick increase in static yield stress, allowing each layer to be built up to support the weight of subsequent layers. So here is one example, a pre-shear, a rest time, ramp up, ramp down. So ramp up is breakdown, ramp down is build up. Structure is breaking down, structure is building up, and you can do, so these are mixes with some little bit of graphene added to see what the effect is. You can see this is OPC, and this is the thixotropy of plain cement paste. When you have a little bit of limestone added, when you have fly ash added, when you have fly ash and limestone added, you can see the effects of adding of these materials on thixotropy. So this is short-term thixotropy, primarily colloidal flocculation. It's by, because at very early ages you really haven't formed hydration structures. It's basically the flocks building, coming back together. You've tried to break them up, they're coming back together. So it's basically flock building up very early ages. With time is when hydration starts to pick up. What happens after extrusion? The mixture needs to rapidly gain stiffness, often achieved through tuning of thixotropic behavior, allowing it to take the superimposed loads layer after layer. This process is called buildability. You can use two different tests to characterize thixotropy. One is viscosity recovery test. The other is static yield stress or storage modulus evolution with time. So remember, again, I'm going back to what we said earlier. We have a bunch of tests that we talked about yesterday. They are all material characterization tests. You never bothered about what the printer is, what the nozzle is, all of that, right? Yield stress, plastic viscosity. From those tests, you derive these properties, which now has some relation to your extrudability and buildability. You see that? Yield stress and plastic viscosity are indirect indicators. Thixotropic behavior are direct indicators of extrudability and buildability. You get some more clarity in the properties that you measure to understand what your material is doing. I'll stop here. Any questions on any of this so far? Yes.
If you are doing extruding, for example, if there is OPC, the initial setting time of OPC generally around 25 to 30. But what if we do the extrusion after 30 or 25 minutes, then we expect it to last year. Longer than that.
Correct. Yeah. So, and that's some of the very important considerations, and that is why generally plain OPC extrusion is very difficult. You always add some other material to it. You pretty much have a supplementary cementing material. You have a chemical agent to change these properties, because if something sets very quickly, you really have no control over it, right? So you do add some other material to delay setting, to ensure that the material stays flowable for a longer period of time. Those are all mixture design characteristics that you have to think of. Pretty much plain OPC printing is non-existent for several reasons, this being one of those. Other questions? We'll talk about interfaces and failure tomorrow. So we'll do the fresh state. We'll slowly build up like kids become old. We'll make sure that we are young enough now. We'll get old tomorrow, day after. Other questions? Not for thixotropic behavior, because what happens is mini slump, you can do it of, well, you can kind of do it, but the problem is the variations are going to be so small that you can't pick up anything. So you can take the test, do a mini slump, you can remix it after half an hour, do a mini slump, you probably will get the same value. It's not sensitive enough to pick up those differences. Because yield stress by itself, yes, but this is not yield stress alone, right? It is that change between the yield stress in the up and down ramps. It is that little difference in the area that we are looking at. So some of the interparticle interactions you might not get it. Yes.
What are the questions you recommend for worksite conditions? If you are going to be mass production.
Um, I have seen, I'll get there when I've seen a few of those. I haven't done any of those. I can tell you that. I haven't done any of those, but I have seen a couple of companies doing a few tests for these. We'll get there. Other questions? All right. So we'll talk about viscosity recovery test, which is a sequence, and this is a very simple test. And what you do is a sequence of steps in your rheometer that mimics extrusion-based printing. So what is an extrusion-based printing? So this is called a three-interval thixotropy test, where you do a stepped-up ramp-up pre-shear. You're pre-shearing it initially, right? And then you are determining and for approximately 80 seconds. So this is homogenization phase. And then you do a low shear rate, very low shear rate. You see that? 0.01 per second for about 60 seconds. This is the viscosity of the fresh suspension before printing. Right? So this is what is the characteristic of the material ahead of time. And then you immediately ramp up very quickly. You get to a high shear rate of 100 per second. What is that? The mixture that was sitting in the extruder is now suddenly being extruded, right? Shear stress is very high. Shear is very high. You extrude it under a very high shear, and that is mimicking the extrusion process. And then very constant low shear rate of 0.01 second after extrusion, it is at rest to mimic that a very, very low shear rate. So this is called three interval. You can see those three intervals, right? Pre-shear to 1, 2, 3. First interval is the basic characteristic viscosity. Second interval is the extrusion process. Third interval is the rest. How well are you recovering the viscosity after this process? Because you have decided a certain viscosity that you wanted and designed the mix for that viscosity. After this process, are you still having that viscosity? If you're significantly losing the viscosity, you have a problem, right? So here is how the results will look like. So here is your initial viscosity, you extrude it, and then you go back at rest. It's recovered all of that viscosity at a low shear rate. You've recovered those viscosity, which is because at high shear rate, you have really low viscosity. Shear thinning, remember? You have a shear thinning material. So at high shear rates, the viscosity is very low. It's just flowing nicely. And then you put it at rest, the viscosity is recovered. So most of it is recovered. You see that? You had about 95% of the viscosity. Notice that this is logarithmic axis, but you have 95% of your viscosity recovered. That's a reasonably good one. Again, here also, your viscosity is recovered. That's one test. Again, a nice qualitative test for you to say what will work or what will not. This is for printed foams, very similar idea. Okay, so what are the implications? High shear rate that simulates extrusion reduces the viscosity by several orders of magnitude, enabling the flow through the extruder. Right? Flow requires low viscosity. High shear rate enables that flow. Further imposition of a very low shear rate reorganizes the particle structure flux, but impedes the complete recovery of viscosity because you're still mixing at a very slow rate. So it's not complete rest, but you're getting there. And theoretically, a material can be considered to maintain its shape if it recovers its initial viscosity after the extrusion process. That's what you want, right? After you extrude through, your screw extrudes your mixture, it comes out through, it has to come out shape stable. If that happens, you can say that this is a shape stable material. Viscosity recovery rate greater than 95%, appropriate build generally indicates appropriate buildability. That's what you do. Now, you need structuration. Here is how we use thixotropy here. You need each extruded layer to maintain its shape under super. It's not enough that you just put one layer and that layer stays like that. The next layer has to come on top of it. And when does the next layer have to come on top of it? Pretty quickly, depending on how quickly you want the structure to be built up, right? If you don't want to build a single story, it takes 6 months to build a single story structure, you pretty much have, at least a couple of feet built up during a day, or 3-4 feet built up during a day, depending on what your design is. So you want this next layer to come on top immediately or very quickly. And as these layers progressively develop strength and stiffness, how these properties are developed becomes important to understand. How do you design your printing rate, right? Then only you will know the extruded layer, how quickly can it take the next layer will tell you when my printer can come back to this location again. How much time do I have? Lots of time this is done through trial and error. You do it several times. Now we are trying to put in some math behind it so that you can reduce the number of trials. Again, the entire idea is not to give you a foolproof methodology where you can close your eyes and print tomorrow. This is only a process flow chart. Like doctors will say, eat well, exercise well, don't drink, don't smoke, do all of that so that you will live longer. Is there any guarantee for that? No, right? You might do all of these and you might not. So, but can you go and blame the doctor? No. So, these are all general knowledge that we know we have to do it, and these are all processes to follow. When a process fails, you can come and ask why my process fails. Now, if all of us do all the things that doctor says, eat well, exercise well, do all of that, and if all of us get sick, now we can go and ask the doctor, looks like you're wrong. You don't have the right idea, right? But if 2 or 3 of us randomly go, you can't really question. So the process is what it is. What I'm saying is that you might follow all of this and you might still fail. That's part of it. You have to correct the process and go. But if you're consistently failing by following the process, you should understand that your process is wrong and you should fix the process rather than saying that none of this works. Because it works, people have done it, you've shown this, right? But this is only setting up that right process. So as it develops strength and stiffness over time, you have to see how the printing paths change. What are the deposition rates? What's my printing rate? What's my speed? What's my nozzle speed? I can't decide my nozzle speed on my own. My printer has to support that as well. Printer has to be able to do that. And I need to be able to deliver enough material consistently, retain the shape, do all of that in a way that is consistent. So structuration refers to the development of mechanical strength in the material over time. Remember, thixotropy is the ability to regain the properties. Structuration is a big brother of thixotropy, which quantifies how mechanical properties develop over time. Thixotropy simply tells you, have you recovered your viscosity? Have I got my static yield strength enough to do it? Structuration tells you, has the structure developed enough mechanical strength to take the next guy sitting on top of me? Clear? So again, two related terms in the broader sense, but in terms of doing the calculations, different, because one is directly relating to the stiffness or strength that is in the structure. Now, you can go back and trace all of it to the interactions between the particles and the hydration and the reaction of particles. At the end of the day, that's where everything converges to. But for the time being, we would just ignore that part, knowing that you're all hydration experts. We would not get there. So it's a critical time-dependent property that allows each extruded layer to support the weight of subsequent layers, essential for ensuring buildability. You see that how structuration now is related to buildability? Only if you have structuration in the layers can you ensure buildability. And buildability also is a very fluid term, because for me, if I'm building a little toy thing in the lab, 4 layers of buildability may be enough. Whereas if I'm building a house, I may need to have 4 layers of 5 mm thickness versus 20 layers of 20 mm thickness. That's where the difference is, right? So you have buildability is a very qualitative thing depending on your application and your printer and all of that. So static yield stress under a constant shear rate, the shear stress of the paste progressively develops to a maximum value with time. So when you do a constant shear rate with time, you get to a maximum value after which it reduces to an equilibrium value. The peak shear stress is a static yield stress, which is a minimum shear stress required for the material to transition from rest to flow, reflecting the internal structural strength. Whatever is the internal structural strength required to transition from rest to flow. So this is some examples of static steel, static strength. You can use the that's growth hydrates. I'll skip that. I'll show you here. Yeah. This is time. This is how much of shear time in seconds you have done. And at different time, you see the shear stress evolving, right? So static yield stress is measured at regular intervals. Pastes are pre-sheared at high shear rates for some time to homogenize. Static yield stress and a constant shear rate is applied for a small time. And then you find out what that, all of you see those peak values in all of these cases here? That's a static yield stress at each of those times. And you find the static yield stress that allows tracking up of the structural buildup. So now we are doing it with time. Now there is a question. How much time will my rheometer allow me to measure this? Right? Depends on the capacity, the torque limit of your rheometer. So if you do a rheometer that has slower torque limit, you might say that, you know what, at 15 minutes, all my calculations are ended. After 15 minutes, don't ask me what it is in my printing. You go find out on your own, extrapolate. But then you need the rheometer to tell you at least to a time where you can think you will print a mix. I mixed it. Do I need an hour to print it? Can I do an hour, 90 minutes worth of measurements? You need to have again, that's again measurement related uncertainties. How much of time do I have to measure? The static yield stress, actually, if I really have, like I said, remember rheology, even rocks flow, even rocks move. So if I really have an infinite torque capacity, I can keep on measuring static yield stress even after this thing apparently has set or hardened. Right? But I don't want to do that. I want to do it until at least I'm able to extrude and a time at which reasonable buildup of strength happens. So this is one way of doing it. Now, where does it come from if you're interested? Combination of colloidal interactions. All of these are flocks or colloids or cement particles are all coming together as colloidal grains. Particles flock together and the particles bridge by formation of reaction products. So that's where all of these static yield stress is coming. Again, like I said, particle bridging is a function of how far away the particles are. How far away the particles are a function of? Function of packing density of particles. Packing density is a function of particle size and size distribution. Now you go back and trace it all the way back to what we talked in the morning. All of this is just one big interconnected family, just that the relatives don't know each other at different points of time. There's long lost cousins. But you go back and trace your origins to pretty much the same place. Flocculation lasts only a very short time after mixing, after which structural buildup is dominated by formation of reaction products. If you have done any course on cement hydration, you would know that flocculation is very early. Once the reaction and reaction products form up, it is structural buildup after that. Okay, so here is again, you can use now this is a good way to document it. Your static yield stress as a function of time will be a curve like that. You can model that curve as a constant plus a thixotropic factor times some classic times, a rust time, a characteristic time, etc. And this A thix is called the structuration parameter. This is related to short-term thixotropy and early age structuration rate. So this parameter is related to the early age structuration rate. So as soon as I have a mix, if I print, If the structuration rate is high, I can come back and put the next layer faster. If the structuration rate is very low, I may have to do more time. So in the real practical world, once you know the structuration rate, it will give you indications as to how you can plan the printing path. Print path planning is also an important thing that people that print multiple structures, larger perimeter structures, really think about. If you're doing a house and all with several walls, you think about which wall, what path to take to come back, and that's a function of structuration rate. How much time would you like to spend between point A and point A when the printer nozzle comes back to that location? So this is a good way to do that. And then suggest the potential for rapid qualification of binders, streamlining the evaluation process. Again, the idea is that you have to have some baseline to see which mix I can print, which mix I can't, which one I want to make changes in. All right, so this is all about rotational rheology. I will stop here for a minute before we get into same ideas with oscillatory rheology, a little more intuitive ideas on structuration and strength development. Questions? Is a lunge or the topic or both?
Living lunch.
Only the lunge, yeah, I know. Can only be lunge. We should have starving courses now. Everybody good with this basic ideas? Again, you can notes, all notes will be available for you. So you can, but again, the fundamental idea is that these are all connected. These are all several different rheological parameters. You may not have to measure everything for all the projects, all the works, right? You need to know which one you want for what application. That is something that you have to do it. To your question on how do I know buildup. So one of the methodologies that I have seen is some non-destructive testing using ultrasonics. Using ultrasonic scanning is one of the things that they have evaluated the structuration rate so that they know how quickly they can build up. There's a handheld ultrasonic scanning thing that I don't think it's accurate. It's as accurate as your contact ultrasonic sensing. This is non-contact sensing, so it'll be a little less one. But I have seen Icon guys, not Icon, Cobot guys use it for build-up rate and say that, and they say that they haven't. So I asked them if they have published it. They haven't. It's all their internal stuff, but they use it to determine the whole idea of printing path. When can I come back idea? So they say that this mix can come back because they use aggregates too now. It's important for them to do it very quickly and rapidly. So they do use non-contact ultrasonics. One way of doing it. I'm sure there are other ways people are looking at too. Other questions? I think it should be made mandatory that everyone should have asked at least one question before you get the certificate, right? Or you can have pre-planted questions. All right. How much time do we have? You said 3:30, right? 45 minutes. So let's do a 5 minute. I need my throat break. 5 minutes. Yeah, that's all I need. I need only half an hour. If you don't ask questions, we'll go even faster. We can finish in 15 minutes and have coffee. Well, I've given you too much of incentive now not to ask questions. Influence of aggregate skeleton on structuration. So structuration, if you look at the way we define it, it is a mechanical property development because of the reaction and network formation in the cement paste, right? So it's a strength indicator at that point. You can't really bring in aggregates there. But I'll show you the way to bring in aggregates is to look at storage modulus. Because aggregates, you can easily use, you have seen all these equations that you've used to find the elastic modulus, whether you can use parallel model, series model, bunch of models using volume fractions, right? So with aggregates and elastic modulus, it generally becomes a really easy volume fraction problem, even though it's not exactly like that. So if you look at volume fraction of aggregates and elastic modulus, if you look at say a parallel model where you say E is equal to E1 V1 plus E2 V2, right? If you do this, you will get something like this. Or if you do 1 over E is V1 over E1 plus V2 over E2, you will get something like this. But the actual data lies somewhere in between, right? But that's okay. You get indicators using either of these models, using volume fractions and the elastic modulus of the individual phases, you get some indication of the composite stiffness. So stiffness, you can't use this for strength, right? You would never use volume fractions for strength. Um, but stiffness, this can be used. Therefore, you don't use yield stress because yield stress or static yield stress is a stress parameter. You don't use a stress parameter, but you can definitely use a stiffness parameter. So using oscillatory rheology, if you find the storage modulus, then you can use G prime and your volume fraction of aggregates to come up with what will be the influence of aggregates on structural rate. Don't use it with static yield stress, use it with storage modulus. Same measurement, very similar measurement, but you can do it very easily. And that is why I keep saying that aggregates is a scaling problem if you know to use the right measurement. But if you use yield stress and try to scale, you'll be all over the place. You will never get it. But with storage modulus, it'll be a nice scaling problem to use. Storage modulus. Hmm? Yeah, stiffness is so storage modulus is the so if you look at um, complex modulus is your storage modulus plus imaginary part of the loss modulus. So this is storage modulus. So you can either use this alone, or if you're really creative, you can use square root of G prime square plus G double prime square if you are really creative. But the problem with using loss modulus is, you remember yesterday I showed you the transitions. The linear viscoelastic range is where your storage modulus is like this and the loss modulus is like this. Beyond the linear viscoelastic range, your things kind of change. So if you start to do this, you don't have this much of difference because these things are kind of overlapping. The balance will go away. But if you just do this, you will see some clear differences and you can keep that. But either way is okay. Really doesn't matter. But it's so easy to just pick this one value and use it, right? All right, ready to go back and do this? Yes.
You mentioned that there is no river. It follows the same path. Like, why does it follow the same path? There is no river.
Did I say it follows the same path back? It should not follow the same path back. It will not follow the same path back. Because if it is so only if it has the same structural property as it was going in the up ramp, in the down ramp, will it come to the same point. If it does not have it, it won't. So it should not. Now, if it has not changed at all, you are getting a material that has no structural change at any shear rate. It'll follow the same curve. Like your elastic modulus, your spring that is extended coming back the same way, right? If there is no structural change, it will come back the same way. The changes are because of structural changes. That happens because of your shear rate differences that you're imposing. Right? So it should not come back. So sorry if I said that it'll go to the same point. No, it should not go to the same point.
Also, like, are there any materials or any cases like that can be higher the second round in base? I have done the initial one.
I don't know. Have you seen something?
So yeah, and I think basically it's about
What are they? Yeah.
that the material is not completely broken down. But makes it better.
No, but you remember we looked at one paper where you were trying to write that paper on cement pay on shear rates, right?
Like
Carbon blacks. Yeah. So yeah, you can have antithixotropy also, but that's not what we are talking about. We don't want that. Other questions? All right. So we'll get into oscillatory rheology or the idea of evaluating storage modulus. Yesterday we talked about applying a small oscillatory amplitude, right? A sine wave function at a very small frequency so that you are not damaging the structure of the material. You are just evaluating the material as it is. That's why oscillators, so small perturbations in strains or stresses, you can do shear stress sweep, strain sweep, or frequency sweep. All the examples I showed you was stress sweep. You're sweeping from 0.1 Pascal to 1000 Pascal or whatever that range of stresses is at very small frequencies, very small amplitudes. You can do the strains from 0.01 to 10%, 100%, 1000% strain at very small values. So you're not doing any breakdown, any structural damage. So a few conclusions that we have seen from our work. Higher storage modulus enables the printer layers to better retain stability and carry on superimposed layers. Should not be a surprise. Higher stiffness, you can carry more load. That's what your structural mechanics have told you all the time. Lower value of phase angle represents a more solid or elastic behavior. So phase angle is the ratio between G double prime and G prime, which is called the tan delta. That's your delta is your phase angle. So lower value of phase angle, lower value of tan delta represents a more solid or elastic behavior. Yeah, because this has to be lower, meaning this has to be lower. The loss component has to be lower, which means it's more solid, right? So again, it comes directly out of that equation. Critical strain, which signifies the end of linear viscoelastic regime. If you remember yesterday, you have the curves going like this, correct? This is your linear viscoelastic range. This is your solid-like behavior. The end of this plateau range is your critical strain that you can kind of indicate as the strain that is the deformation capacity of the specimen. So at what strain would you deform, which is an indication of how much load you can carry before it strains too much. So critical strain can be used for that, because when the critical strain is higher, means interparticle connections are much stronger and there is more bridges. Critical strain is lower, the solid will tend to become a fluid, tend to move and deform much faster. So you can use oscillatory rheology as some indicators for material delivery, extrusion, layer buildup, and all of that. Here are a bunch of examples where graphene was used in 3D printed concrete. You can use storage and loss storage modulus, G prime, and the G double prime values here. The phase angle goes down as the material becomes more and more solid. So adding more and more graphene gets more rigidity to the structure. Phase angle goes down. Critical strain goes up because material behaves more solid. So again, all these parameters telling you roughly the same thing, but different ways of measuring it. Again, influence of binder composition, different binders, OPC versus fly ash and limestone, different water cement ratios. You will see how the storage modulus and loss modulus changes, phase angle, critical stress, critical strain, all of that. So it's very similar ideas.
saturation, we can add slack. Middle add, so we can add slack.
Yeah. So if structuration is that early development of that network and strength once you have it at rest, the building up, right? whatever does its slag or whatever accelerating admixtures will do it. And that's why sometimes you add this at the end of the nozzle so that it gets quicker. Anything that accelerates hydration, if you pack the particles much better, it'll do the same thing. Slag can react faster and do. So lots of these materials can do it. So whether it's by particle reorientation mechanisms or by hydration, you can do all of that.
If you add accelerated heavy housing,
So that's why these two case systems, right? So you can't add accelerator along with the mix. So as the material comes out of the nozzle, you spray the accelerator.
just spray.
Just spray, yeah, spraying of the accelerators. No more. No, you can't mix anymore, right? When it's coming out of the nozzle, you can only spray. So basically, what you're getting is your surface layer being kind of stiff enough to carry it. It's not completely happening because it's only accelerating on the surface. But that's good enough to retain the shape and be able to carry the next layer. Storage modulus evolution with time. So if you do a small strain test, you can do storage modulus as a function of time, and you see how this is only about for 30 minutes, 1800 second. I think I have another picture that goes to 180 minutes. You see how storage modulus starts to evolve with time for different types. So this is OPC. Those are the other mixes with other materials in it. But you will see that storage modulus start to increase with time. And that you can see the same kind of equation that I showed earlier for thixotropy. Right? Very similar kind of equation. The only thing is the constants are slightly different. So you can have the storage modulus as a function of time expressed by this equation. So where C is the amplitude of flocculation recovery, which means how much of the structure is recovered with time. Lambda residual is a residual structural factor after pre-shear. But this is the rate of G rigid is a rate of structural buildup due to hydration. So now this will be different depending on what materials you have in the mix. With fly ash or slag or silica fume, this value will be different, and you can find all these constants. You can simply fit this as a function of time. You can get all these constants that will give you an indication of how the storage modulus is evolving with time. Now, once you know how the storage modulus is evolving with time, you can play around with simply the fact that storage modulus of paste is what you have determined, or mortar if you did the mortar test. Any inclusion is nothing but inclusion modulus added to the equation. And you can do that and get the values. Again, flocculation recovery after pre-shear, structural buildup due to hydration. So higher value of C means flocks are capable of recovering faster after imposed pre-shear. Higher lambda value indicates a more interconnected structure. Faster buildup results in lower theta. Higher value of G indicates a faster structural buildup due to hydration. So all of this, again, as indicators as to how your structure builds up. Another example of storage modulus buildup, all the values that you see. And then this is your till 30 minutes. If you have a rheometer capable of shearing a paste even beyond 30 minutes, right? Or if you cheat the system by dropping the water cement ratio or increasing the water cement ratio and make the mix work for a longer time, you can do whatever you want. You can do this for much longer. So here we cheated it from 0.3. It was only getting up to 30 minutes and the machine said, I can't do this afterwards. So you do a 0.45 so that the mix remains fluid and the system can measure for longer time. You get storage modulus as a function of time. And you can see here from 30 minutes to 3 hours, your storage modulus increases by more than 2 orders of magnitude. Very quick structuration rate, right? Which means what? How much you can carry at 30 minutes versus how much you can carry at 3 hours is much higher. So in that 2-hour gap, so you don't have to wait till the next day. In that little 2-hour gap, you have 2 orders of magnitude increase, which means you can actually play the system really well to find out when you can start building up. So this is an advantage of understanding storage modulus evolution. And then there is something that we have done where we're looking at oscillatory rheology as one test that can do top to bottom of everything. So you can do storage modulus can tell you indicators about dynamic yield stress. It can tell you plastic viscosity. It can give you indicators of static yield stress. It can give you hysteresis or thixotropy. It can give you structuration. Again, within all of this, we'll have to take with a grain of salt. Within the range of parameters, we are trying to see if there is one test. To your question again, if there's one test that rather than doing all of those, I don't know if it is certain, but I think at this point, I believe that oscillatory rheology is something that can cover a lot of bases with respect to understanding how a mix will behave. Again, there might be other tests. I'm sure there will be other tests. There will be other ways of doing it, but at least in a very nascent field, rather than measuring 200 different parameters, if there is one test that I can do to do early age meaning immediately after mixing, and to find some indicators of buildability, at least oscillatory test is one of the mechanisms that you can use. Not by itself, but by doing time-dependent oscillatory rheology and getting some storage modulus evolution, all of that. So generally, some indication of what it is. Now, we have done some really interesting work on rheology hydration link, and how do we do that? So, and how do we actually measure it? So we brought in one more test, which is an easier test to measure. So you do rheology, you get all the rheological parameters, you get hydration. Hydration and rheology are connected for all the reasons that we talked about earlier. Rheology is about particle linkages, particle connections. Hydration happens much more when the particles are connected more, and when the particles have started to develop the interconnected network, and hydration proceeds, rheological characteristics go down. So you can really get a good relationship between rheology and hydration. So if you look at storage modulus as a function of time, you will get a curve like this. And if you look at storage modulus as a function of cumulative heat at that time, you will get a curve like that. They look fairly similar if you have a decent enough eye to look at it, right? So you have storage modulus as time versus storage modulus versus cumulative heat. So cumulative heat may be some way to measure it. So if you look at doing it, so here is your induction period, right? Nothing is happening. And this is all dissolution. So we really don't bother too much about dissolution. That's anyway happening. Acceleration is where you actually start to produce your hydration products, and your initial set is somewhere at the early part of your acceleration curve in your hydration curve, if you know that. So if I do that, so that's your heat release, that's my cumulative heat. And then if I subtract my heat at the onset of acceleration, and then here is my G prime plotted as time, and then here is G prime over G prime naught, some randomized normalized value and a normalized heat, they fall along a straight line, right? So this is the idea that you can relate rheology and hydration. You can obtain indicators of rheological measurements from hydration or vice versa. What we did is went in one step further and said, both these measurements are difficult. Even hydration with an isothermal calorimeter and doing all of that, putting all of this, rheology, putting the paste in the rheology is different. Can I do something even more easily? And one of the easier measurements to make is an electrical measurement, just to measure electrical conductivity. So the question is, can electrical conductivity tell us indicators of rheology and hydration, including storage modulus? So what happens? Here is how it is happening. This is just a schematic curve. That's your hydration curve. So the dissolution, induction period, and acceleration. So here is where acceleration starts. Here is your storage modulus evolution, almost nothing until acceleration starts. Remember, storage modulus also is network has to build up, acceleration has to happen. So that also happens in the acceleration range. And here, look at electrical conductivity. You have initial conductivity increase because all the ions are dissolving in the solution, but then the conductivity starts to suddenly drop when the reactions and the accelerations start to happen. Everything has some kind of a fluctuation in that acceleration window. So if I can pick up rheological changes and hydration changes and easily measure conductivity, hey, maybe conductivity is a quick and dirty measure to figure out how rheology and acceleration changes. And unsurprisingly, actual results also are like that. So here is your heat flow curve um, for OPC and some other mixes. And here is your electrical conductivity that changes with time. Here is your heat flow for another set of mixes. Here's your storage modulus as a function of heat, total heat minus heat at acceleration. So just at the onset of acceleration. And that, look at storage modulus versus conductivity minus conductivity at the acceleration state. So this and this are extremely identical, and I can plot it fairly consistently. So cross property estimations is something that's a very interesting field, so that you measure one and you infer so many other things from it. Interesting way to see. So the reason why electrical conductivity is very appealing is that there are a lot of applications for which conductivity is used already. So for durability, one of rapid chloride permeability, all of you use RCP method for durability, right? Rapid chloride permeability is nothing but a conductivity method. It's a glorified conductivity method, which makes things actually worse and wrong, in fact, by putting in very high voltage and things like that, right? So RCP is an actual conductivity method, and in the US, we have gone away from RCP method. Now we simply do, why waste 6 hours and 60 volt of potential? Don't bother. Just take a DC measurement, a 2 point or a 4 point DC measurement instantaneously, and move on with life. That's good enough. And they are now relating that to all durability parameters. There's an even ASTM standard for electrical conductivity based measurements of durability. So electrical conductivity can do durability very well. There is a whole sort of studies where electrical conductivity is linked to hydration, kinetics, growth of products, all of that. There are sensors, electrical conductivity sensors that have come in to measure hydration, simply looking at changes in conductivity over a period of time. So it's not impossible that if you are interested, if you have enough sensors, it's not impossible to actually track buildability and extrudability through electrical conductivity. That'll be a very interesting thing. I want to do it, but I'm too bored and busy with doing other things. I haven't been able to do it. But that'll be an interesting work to do if you can measure, because once you track rheology, which you can, once you track hydration, which you can, there is no reason why extrudability and buildability cannot be inferred from conductivity measurements. Maybe not simple conductivity, but maybe some impedance kind of measurements. Maybe using, there's no way that you cannot. That's my feeling. I haven't really done it, but I will have to do it at some point of time when my students are happy enough to do more work. But this is something that is probably from a testing point of view, from a quick quality control point of view, because electrical conductivity, electrical impedance measurements are becoming quality control tools very fast, and it's very cheap too, or reasonably cheap too. So that's one place to go. You said 3:30, right? It's only 3:15, so we have enough time for questions. I think I have. So here is a recap. Everything that we have done so far in one slide. If you have been dreaming so far, at least you will hear the highlights. So a lot of rheological tests we have talked about, right? Today's quiz has all of this, right? All the rheology tests in this quiz. So we'll know if you have paid attention. So host of rheological tests to cater to specific performance aspects. So let me do a quick quiz before a quiz, because we have time. Just you don't have to test big. Yeah. We will give you all of those. Don't worry, we'll give you. So by the time this whole thing is done, you have all the notes, right? It's just PDF. You can make it into PDF, and everybody will have access to all. Yeah, so don't worry, you have access to all of this. If you want to keep a notes and take notes of important points, it's always useful, but don't have to take screenshots. You will have all of this for you. right? So host of rheological tests for specific performance aspect. So can somebody tell me what all rheological performance measures we did from yesterday until now? We did a lot of it. And no answer to this question will be I'll have to leave today. What are some of the rheological tests that we did or performance measures that we looked at? Yield stress. How many yield stresses? Two. Why static? What will static tell you? Gives you an indication of structuration from rest. So it's a buildability characteristic. What will dynamic tell you? The ability to flow or the onset of flow. Okay, so two yield stresses. Great, everybody remembers that. What's next? Viscosity. What will viscosity tell you? Ease with which will something will flow, right? You can quantify how quickly, how fast, how well something will flow. So one viscosity, two yield stresses. What else? Storage modulus. What will storage modulus tell you? The structuration, the rate of development of properties with time. Okay, what else? Loss modulus will tell you um, the fluidity or the opposite property, the damping property of the material or the energy absorption property or the softness of the material. Not much use though. Phase angle or tan delta, the ratio of loss to storage will tell you again how quickly the structure is developing or not. What else? Thixotropy, I forgot that. What will thixotropy tell you? The ability to regain, break and regain, right? Rebuilding kinetics. What else? And thixotropy can be connected to yield stress as well because you can use it through yield stress. What else? That's it. Structuration rate, which is again how quickly the strength will develop, which can be related to storage modulus as well. So those are all the general rheological characteristics that we talked about. Because now we are going to, so all of this is, you can think about 3D printing or not think about 3D printing. If you think about concrete rheology, all of these are important, right? With 3D printing, we kind of related why these are important with respect to layer building kinetics. Now, in the next set, probably tomorrow morning, we are going to look at how extrusion process itself, and remember I told you all that we talked about are of materials. This has to be connected to, what are the two other things? Printer characteristics and process characteristics. I don't know printer characteristics. I have no idea what the printer characteristics are, but I can make some informed decisions about, well, this will be the nozzle, this will be the kind of pressure that the printer will exert in getting the material out. I can do some kind of generic stuff, right? So with respect to the printer, I will simply think about what I call an extrusion pressure. No matter how the extrusion pressure is applied, I will simply talk about an extrusion pressure. Once the material that has put in the extruder has to come out, whether you're shearing it with a screw, pushing it with a ram, pumping with oil, or you're blowing on your own energy, it has to come out, right? We will simply call that an extrusion pressure. And we'll use the most simplistic method to quantify that extrusion pressure so that we understand what that mechanics is. With respect to printing parameters, we will look at the printing speed, how fast you are printing, the layer build-up rate, how quickly you want to build up the layers, and then as process parameters, we will look at layer heights also, layer widths and layer heights, layer geometry. That is for tomorrow morning. Right? So right now you have a good handle on all these parameters. Now we will put all of those in a jar, blend together, and then put it through an extruder and get extrusion pressure, velocity, again, pressure velocity relationship. So we'll go through some very basic physics that I'm sure you've forgotten or you didn't want to see. We'll see some of those. I'll show you some very common equations that are used in traditional fields of extrusion, whether it's polymer extrusion or clay extrusion, some of the very classic equations that relate pressure to flow, right? Now we're talking about pressure. So far, pressure was some kind of, yeah, I need pressure to get this out. But in my rheology, in my obsession with yield stresses, I forgot about all of that, right? Now I'm actually going to introduce the idea of how do I exert a pressure? How do I get this thing out? How do I print this? And what are the parameters that are important? There also, it is important that what we are going to see are guidelines and broader parameters. It will change with specific extrusion pressure applied by a specific printer in a specific environment using a specific mix, right? If this is not there, none of us will have jobs. So we should be thankful for the complexity that concrete offers us. This is what I'll tell my first class on concrete. You should be thankful for the complexity. It'll be hard to study the class. It'll be difficult. Why are we dealing with a complex material? You should be thankful because that's giving us jobs. That's keeping us gainfully employed. That's why there are problems. People don't understand why things are failing, why things are cracking. We all will have jobs, right? So it is a complex system, but we'll try to make it simple to go through that process. But again, keep in mind that if you consider this entire topic as walking up to the top of Himalayas, or if you're doing an Everest climb or whatever, all we are doing at this end of the week is telling you that eventually you have to get to 25,000 feet. At 10,000 feet, there is a base camp. You might get water and some refreshing stuff there. And right now, once this week is done, you might get some Sherpas to help. That's all we are doing. Nothing more than that. Okay. So if you think that we are in the Everest, well, you both of us are there. We are there. If we are useful or not, they'll have to decide if the Sherpas are useful. But that's all we are doing, right? The field is vast. There is explorations that all of us have to do on our own. On that note, if you have any more questions, I'll take. If not,
So
yes.
when we talk about this electrical resistivity measurement, so how would we correlate the resistivity with the hydration? Like there were some peaks in the quantitative.
Which peak are you talking about? Let me show you.
What are the
Oh, okay. So here, this is your electrical conductivity. So as you start measuring electrical, you mix cement and water, instantly the conductivity slowly goes up because ions from cement are coming into the solution. So the solution is becoming more and more conductive. The conductivity keeps going up, right? But then when the induction period is done, when the acceleration period starts, that is when the cement grains are starting to hydrate, the hydration products are starting to form bridges. That is now breaking the connected channels that goes and increases the conductivity. At that point, the conductivity starts to come down. So this is where conductivity starts to come down after your reaction products have started to form. Similarly, same corresponding to that same, because the reaction products have started to form, your modulus have started to go up. That's what you see in the bottom line. And because your reaction is happening, your heat is also increasing. Until then, that's the induction period where nothing happens because of the effect of gypsum that you add in cement. And then you have your induction period. Okay. Other questions?
So is more of a DC based or is it impedance spectroscopy?
No, this is impedance spectroscopy, and we took the bulk resistance from the arc. Generally, bulk resistance corresponds to, in lots of cement-based work that we have done, bulk resistance corresponds to about 100 hertz DC, 100 hertz measurement, and it's a direct DC measurement. So
100 hertz frequency.
yeah, the RB, the bulk resistance is about 100 hertz frequency. Generally.
Part of doing kilohertz radians thing where we are like finding a difficult getting a field transition, whether it is electric.
But you can do, if you do impedance, you will get it, right? Because if you do in impedance, you actually will get, you will get the bulk arc and the electrode arc, and this is your RB value. And once your RB value, you can simply call that as a resistance and calculate it.
But again, the value kind of shifting.
It will shift with hydration, right? As you starts hydration, it'll keep going this way. Yeah. So that, and so you will keep taking this value, but the frequency that this appears generally doesn't change.
So
Generally, I mean, there might be some changes.
actually, this is
Yeah, this is the electrode arc, right? So this is the bulk arc. That's the electrode arc, right? So you want to maximize whatever you get here. I mean, even if that's not the case, it's okay. Even if you get an arc like this, that's okay. You can get that value. The reason why you can't do too much of analysis if you get this is because you don't know where the center of this imaginary circle lies, and that is where you want to have the calculation for the phase angle. So your phase angle calculations will be wrong if you don't know where that is, and that's where extrapolation becomes difficult if you don't have a good part of the arc. So they say at least want a semicircle, but it's hard to get that unless you have, because you know that, right? Your frequency is increasing as you come here and here. If you have only a megahertz, you will only get here. By the time you get here, it's in the gigahertz range. It's difficult to measure.
is it like we have
To a test procedure and protocol is very important. You can't do shear rate control today, stress control tomorrow, something else day after, and says I'm getting three different values. You will get three different values. Um, Interpreting material behavior across multiple tests can sometimes yield conflicting conclusions, further complicating decision making. This happens all the time. When we have all the toys, you don't know which toy to use, right? And then you get confused. So it's important to stick to a certain way. So way forward, different parameters mesh provide valuable insights. Small amplitude oscillatory test or the oscillatory rheology that I told you allows continuous monitoring, so it's good. To fully validate any approach, you need lots of data. We don't have that much of experimental data. Standardization of test protocols is very time consuming, but doing that would be highly advantageous for the industry, paving the way for more reliable standards. Again, all of these are things that we have to do it. And if many of you are working in this area, you guys are doing it, collectively, we will get to some place at some point of time. That's the whole idea. So, basic rheology, we have concluded. Tomorrow, we'll do this not very common field. Now with 3D printing, people are doing it, but in concrete, nobody ever talked about it, which is extrusion rheology. We'll spend an hour tomorrow morning on that to link, again, generally all these different parameters. Good? All right. If no questions, we will break for coffee.